I think we won't have questions after that. Ronnie, please go ahead.
Yeah, thank you very much. Thank you for the introduction. We see. Okay, so my talk will be about the multi-GNSS orbit and clock combination. And just to start briefly, the idea of combining AC contributions to the IGS was initiated in the early days and years of IGS. And along with the development of multi-GNSS constellations, some other groups just started independent actions toward the developing of a new concept of multi-GNSS, or the orbit and clock combination, consistent clock and orbit combination, focused on multi-GNSS constellation. And in 2022, IGS called for experts to join a new task force aimed at enhancing IGS product combination within the multi-GNSS framework. And the goal of this action was to develop a workflow for delivering official and final fully consistent multi-GNSS orbit and clock products. And this is the general workflow. I will start with the orbit combination, and this is the general workflow of this process. So we'll start with a kind of pre-check, then we have the orbit alignments, then we have to define the core data set of satellites, so it means exclude outliers and define the satellites to be used in the estimation of the weights, and then we estimate the weight itself and then combine the orbit as a weighted average. But like I said, there are some different groups who worked on that, and they propose different ways of handling outliers, or we have to define the satellites to be used to estimate the weights, and there are some groups who use the so-called AC constellation specific weights, so the weights are estimated for each constellation, or IGS ACC initiated the estimation of AC specific weights, so the weights for each satellites individually. And we need to also define how to estimate the weights. So IGS and Wuhan used the squared inverse of the mean absolute deviation, while the GFZ team developed the workflow based on the least square variance component estimation. But in this presentation, I will mostly focus on these aspects, so how to define and what's the impact of different definition of the satellites to be used for the estimation of the weights. And based and taking benefits of all these findings from this combination task force, we developed the SPOCC software, which mostly inherits from the work done by Gustavo Mansur in his PhD and some previous activities of GFZ, but with some further improvements which we did in the last months. So in this exercise, I use half a year of orbit and clock solutions provided by CODE, ESA, GFZ, CNES, JAXA, and Wuhan. So one slide about the weighting scheme itself. So as for the methodology, we adapted, for the BC, we adapted the methodology introduced by Fürstner, who found an efficient way, iterative scheme of finding optimal variance factors, and just in brief, how it looks, how it was adopted for this combination of the orbits. So we initialize variances, then we calculate the mean orbit, then iteratively update variances to stop the iteration if there are massive orbit differences. It satisfies our threshold. So this is the first result for the combination in the constellation specific scheme. So the weights are estimated for each constellation, and here is the example of here is the composition of the weights for Galileo, BeiDou, and GPS, and the RMS of difference between the AC contributions and the combined orbit. We'll be using this kind of plots in the next slides, just for comparison. So this kind of approach requires general consistency, so we have to, or the robust way we define the core data set of satellites. And we know from previous presentations given today that the orbit modeling quality varies by AC and satellite type within constellation, especially for BeiDou, but also for Galileo. So isn't that just more intuitive to divide the constellation into subgroups by their types? So this is an example of Galileo. Here we have the weights the composition of weights for different ACs when treating the Galileo as one dataset of satellites. And that's after the splitting the satellites into types of FOC and IOV satellites. It agrees well for FOC satellites, but the weights for each AC differ when we separate the constellation into types. And the same applies for BeiDou. Here is the constellation-specific weighting, and after splitting into the subtypes, these are not all the subtypes of BeiDou satellites, but these are just the examples. So we can go even further. So we can estimate the weights for each satellite individually rather than grouping the satellites into constellations or the types. But if we compare the approaches, so here we have for Galileo the constellation-specific, type-specific, satellite-specific, or here like GPS or BeiDou in the middle, the less data, the greater the noise. But is that really noise? So to find out that, we took the time series of the weights for individual satellites, grouped them by systems, and prepared a kind of log-specific average periodograph of satellite-specific weights. And the overall shapes are well approximated by the power spectra of white noise plus power low noise processes, which is given with this black solid line. But most prominent signals are system-specific artifacts, like for example these, like for GLONASS 4 and 8 days, and all the other for different systems. And all these peaks have origin in orbit modeling, which were elaborated in different studies. So if we consider all these high-frequency signals as undesired, we can put this cutoff between desired and undesired signals, which is marked here with a dashed line. And we try to come up with an idea how to get rid of these undesired signals, if we consider this undesired, and we prepare the modification of this versionary iterative scheme VCE with the introduction of a priori variance factor. Just in brief, again, we initialize variances, we calculate weighted mean orbit, and then iteratively update variances. But this is the modified part because we introduced the a priori sigma variances, and to allow for variability of the variance factors, the weights of a priori information can be down by a factor from 0 to 1, and then we again stop the iteration if the RMS of orbit differences meet our threshold. So what can be the source of a priori variances here? We first approach that we found is the sequential approach, in which we take the variances from the previous day to the current combination, and it should work like a low-pass filter, but it needs a special handling when AC was epoch-wisely excluded. And the second option we tested is the incorporation of information from satellite laser ranging validation. And how can we do that? Like here we have the heat map for the example of Galileo FOC satellites, we have the heat map of standard deviation of SR residuals for different ACs in different ranges of beta angles of the elevation of the Sun above the orbital planes, and we can simply convert these to the weights and introduce the process as a priori. And it introduces independent information to the process, because we took this from independent SLR validation, but this had to be, we need at least a year of archived data, and it assumes that the orbit modeling hasn't changed, and it's available only for Galileo and BeiDou, because for these we have the SLR observations. So this is something that you've seen already, but let's compare it with the sequential approach. And indeed, we smoothened this day-to-day variability with the sequential approach. And the second approach of incorporating a priori variance factors based on SLR, we somehow constrained the weights to the values from SLR. And finally, we wanted to evaluate the quality of these different approaches, and first of all we had a look at the SLR validation results, and this heat map presents the standard deviation of SR residuals for different individual ACs, for different types of satellites, and compared it with the different combinations of constellation type satellite, sequential and SLR based. So first we can see is that the quality of the combined solution matches that of the best individual AC solutions, and using satellite-specific weights yields slightly better results than constellation or type-specific strategies. And the sequential weighting that we introduced slightly improves the solution. However, the improvement is rather marginal. And if we have a look at different combinations, the difference between them are up to 2 or 3 millimeters. The next measure of quality that we did are the orbit disclosures, and these are relative changes of this orbit disclosure between different AC, different combined solutions for different types of satellites, and we selected the approach with the constellation-specific weighting as a reference. And first, the green cells mean that the solution is better than this, and the red one means that the solution is worse. And first we need to notice that using multi-GNSS arcs as CODE and AAC do yields better results than single-day solutions. These are here. And except for CODE and EAC, the combined solution is superior to individual solutions. And for GPS, for combination outperforms IGS final, which is here at the end. And the constellation-specific weighting is better for GPS here, while the satellite-specific weighting and type-specific weighting performs better for less uniform constellation, especially BeiDou. And using sequential approach has rather minor impact in this case. And I just wanted to switch to the topic of clock combination, because this is also possible in the SPOCC software that we developed. And this is the general workflow, and you will find more details in the paper below. But just to mention that at the current stage of our software development, only constellation-specific weighting is possible. But just wanted to make you aware that we are able in SPOCC to combine both orbits and clocks, which allows us to perform PPP validation of our solutions, and we did it with kinematic PPP solutions, used GNAT software with float ambiguities, 5-minute intervals, and selected 25 distributed stations. Here we have the results of GPS-only solutions and GPS, GLONASS, and Galileo solutions for north, east, and up components, and the combined solution is the most left. And the key message from here, because I'm run of time, that our solution is comparable with other solutions, but we didn't say the final words because we're still working on the clock combination. And conclusions. So I'm out of time.
Yeah, more or less.
Okay. So maybe just the final, the SPOCC software enables consistent determination of orbital clocks products, and the software will be available upon request, and we are open to discussion and concept for improvements. And improvements of the software are still pending, but thank you very much.